Did you know that our sun, a seemingly ordinary star, is actually a celestial dynamo that converts 600 million tons of hydrogen into helium every second? Indeed, this radiant orb that hangs in our sky is far from ordinary. It is a G-type main sequence star, or what astronomers call a G dwarf star, a classification that speaks volumes about its size, temperature, and luminosity. The sun is a solitary entity in the cosmos, nestled comfortably in the Orion arm of the Milky Way galaxy. Yet, its influence extends far beyond its immediate vicinity. This is largely due to its colossal energy production, which results from the process of nuclear fusion. This intricate dance of atomic particles powers the sun, transforming the simple hydrogen atom into the more complex helium. So, in essence, our sun is a gigantic nuclear reactor, converting mass into energy at an astronomical scale. Delving deeper into the sun's core, we find an intricate ballet of particles governed by quantum mechanics and nuclear physics. This is not a dance choreographed by mere chance, but rather an enduring sequence of reactions known as the proton-to-proton chain. This chain reaction is the primary energy-producing process within our sun, a stellar forge that sustains life as we know it. The proton-proton chain begins with two protons colliding at high speeds. These protons, being positively charged, naturally repel each other due to the Coulomb barrier. However, a phenomenon known as quantum tunneling allows these protons to overcome this barrier and fuse together. This is where the magic happens. Quantum tunneling, a principle rooted in the world of quantum mechanics, permits particles to traverse seemingly insurmountable barriers. It essentially allows our sun's protons to get close enough to fuse into a heavier particle, a process that would otherwise be impossible. This fusion of protons forms a deuteron, releasing a positron and a neutrino in the process. The released positron soon encounters an electron, and the pair annihilate each other in a burst of energy, producing two gamma-ray photons. These photons, trapped within the dense solar core, may take a staggering 100,000 years to reach the sun's surface. During their journey, they are absorbed and re-emitted countless times, gradually losing energy and shifting from high-energy gamma rays to lower-energy visible light. Simultaneously, the neutrinos, virtually unimpeded by matter, zip straight out of the sun at nearly the speed of light. These elusive particles, detectable only through their weak interactions, offer us a real-time glimpse into the sun's fiery heart. Meanwhile, the deuteron collides with another proton, forming a helium-3 nucleus and releasing yet another photon. When two helium-3 nuclei collide, they fuse to form a helium-4 nucleus, releasing two protons and even more energy. This cycle repeats over and over, with each reaction contributing to the sun's ceaseless luminosity. Thus, the sun's radiance is a result of a convoluted dance of particles, a testament to the marvels of quantum mechanics. The sun's core is a subatomic stage where particles pirouette in a cosmic ballet, forging light and life in their wake. Our sun, like all stars, is on a journey of cosmic evolution, with a life cycle spanning billions of years. From its fiery birth in a nebula, through its vibrant youth and middle age, and into its peaceful twilight years, the sun's life is a tale of transformation, dictated by the inexorable laws of stellar physics. Stars, these celestial bodies, are born, live, and die just like living organisms. Sun, our very own star, is currently in its main sequence phase, the longest stage in a star's life. It's been burning hydrogen at its core for approximately 4.5 billion years, converting it into helium through nuclear fusion, a process that releases an immense amount of energy, warming our planet and making life possible. However, like all good things, this phase must come to an end. The Sun's hydrogen supply is finite, and once depleted, our star will undergo a dramatic transformation. It will expand into a red giant, its outer layers swelling to such an extent that it could engulf the inner planets, including Earth. In this phase, the Sun will be burning helium in its core, producing carbon and oxygen. After this turbulent red giant phase, the Sun will shed its outer layers, leaving behind a dense hot core known as a white dwarf. This stellar remnant will slowly cool over billions of years, its once brilliant light fading into the cosmic background. Now you might wonder about the implications for our solar system when the Sun exhausts its nuclear fuel. Well, the transition to a red giant will likely render Earth uninhabitable long before the Sun becomes a white dwarf. The intense heat and radiation from the expanded Sun would evaporate our oceans and strip away our atmosphere. Even in its eventual demise, the Sun will continue to astound us, reminding us of the fleeting yet extraordinary nature of stellar life. This cycle of birth, life, and death is not unique to our Sun. It's a cosmic ballet performed by all stars in the universe, a dance of energy and matter across the vastness of space and time. The Sun does not exist in isolation. It profoundly influences our home planet and the rest of the solar system. Our radiant Sun ceaselessly emits a stream of charged particles, a phenomenon known as the solar wind. This isn't a gentle breeze, but rather a turbulent, high-speed torrent with velocities reaching up to a staggering 800 kilometers per second. This solar wind is not uniform. It fluctuates, sometimes bursting into intense gusts, which can have far-reaching impacts. In addition to the solar wind, our Sun is also the source of other, more dramatic phenomena: solar flares and coronal mass ejections. Solar flares, the most powerful explosions in the solar system, release energy equivalent to millions of hydrogen bombs in a matter of minutes. Coronal mass ejections, on the other hand, are colossal eruptions of plasma, spewing billions of tons of the Sun's outer atmosphere into space at incredible speeds. Now, these solar flares and coronal mass ejections, coupled with the constant solar wind, create what we refer to as space weather. This is not weather as we experience on Earth with its rain, wind, and snow, but a state of the space environment influenced by solar activity. Space weather can affect not only the solar system, but also extend its reach far beyond into the interstellar medium. The effects of space weather are not confined to the cosmos. They can also have significant impacts here on Earth. The interaction of solar wind with Earth's magnetosphere can lead to geomagnetic storms, which can disrupt power grids, interfere with satellite communications, and even pose a threat to astronauts in space. Furthermore, the energetic particles from solar flares and coronal mass ejections can cause spectacular displays of auroras, painting the polar skies with ethereal lights. But they can also pose a radiation threat, particularly for spaceborne technologies and space travel. Indeed, the Sun's influence is ubiquitous, shaping the space weather and casting its effects far into the cosmos. So, while we bask in its light and warmth, let us not forget the tremendous power and influence our Sun wields, both near and far. Our neighborhood of stars is a surprisingly sociable place. While vast distances separate them, by cosmic standards, they're practically next door. Here's a peek at some interesting neighbors of our Sun. Alpha Centauri system. This triple star system, just 4.3 light years away, holds the title of closest star system to us. It's actually two main stars, Alpha Centauri A and B, orbiting each other closely, with a faint red dwarf, Proxima Centauri, farther out. Proxima Centauri is technically the closest individual star at 4.2 light years away. And it even has an exoplanet orbiting it, Sirius. This brilliant white dwarf, the brightest star in our night sky, might seem close at 8.6 light years away, but it's actually just a lone ranger passing by our neck of the woods. Sirius is fascinating because it has a white dwarf companion, Sirius B, which is the leftover cinder of a once massive star, Barnard's star. This tiny red dwarf, a mere 6 light years away, holds the record for the fastest proper movement across the sky of any star visible to the naked eye. Despite its proximity, it's too faint to see without a telescope. These are just a few of the interesting stars relatively close to our sun. Our galaxy, the Milky Way, is teeming with billions of stars, each with unique properties and stories to tell. Our journey into the heart of the sun reveals a celestial powerhouse, governed by the laws of physics and nuclear fusion. Let's revisit our cosmic voyage. We've delved into the sun's core, the theater of nuclear fusion, where matter transforms into energy. We've journeyed through its life cycle, from stellar birth to a future white dwarf. We've witnessed its profound influence, shaping the solar system through solar wind and space weather. Scientists are trying to replicate this stellar process here on Earth to create a clean and virtually limitless source of energy, fusion power. Think about it. Clean. Fusion doesn't produce greenhouse gases or long-lived radioactive waste like nuclear fission. Limitless fuel. The fuel for fusion, hydrogen isotopes, deuterium and tritium, can be extracted from water, making it a practically endless resource. Abundant energy. A tiny amount of fuel can release a huge amount of energy, potentially solving our energy needs for centuries to come. However, achieving sustained fusion on Earth is a huge challenge. Scientists are working on creating and confining superhot plasma, charged particles, long enough for fusion to occur and generate more energy than what's put in. It's a complex scientific endeavor, but the potential rewards are so significant that research is constantly progressing. So the next time you look up at the sun, remember, it's a giant ball of fusion power, and scientists are working hard to bring a piece of that star power down to Earth. So, while the sun may seem ordinary, it is indeed a celestial dynamo. Its mysteries continue to captivate us, illuminating our understanding of the universe. If you're led by your curiosity, hit that like button and subscribe to SciSips for more stellar content. So, what do you say? Feeling starstruck? Smash that like button and subscribe to SciSips for more cosmic adventures. Let us know in the comments. What's the coolest fact you learned about stars today?
Alright, Sci-Sippers, before you go hurtling back into the real world after this epic scientific odyssey, I want to take a quick moment to chat. Building this channel, bringing you these videos, and exploring the wonders of science with all of you is a blast. But to keep the scientific adventure going strong, your help is essential. Liking this video lets YouTube know you enjoyed it, which helps the algorithm share it with more curious minds like yours. Subscribing to the channel ensures you never miss a future science bonanza and lets you know when we upload new content. But the real magic happens in the comments. Leaving a comment, whether it's a question you have, a mind-blown reaction, or even a suggestion for a future topic, is like rocket fuel for the channel. It helps us understand what excites you and allows us to create even better videos that cater to your scientific interests. So, smash that like button, subscribe for more, and leave a comment below, letting us know what you thought of this wild ride through science. Thanks for joining the Sci Sips fam, and until next time, stay curious.